Hey everybody, thanks for tuning in. So just to give you a brief overview on where we're headed for this lecture series, we're going to be answering two questions. Where are we, as in are we located relative to everything else in the universe, and when is now? Because the universe has a specific age, and we want to be able to put our history in the context of the history of the universe. And so in order to do that, the first step is that we have to learn about how we measure distance scales in astronomy. And in this discussion, you guys are going to find out that distance and time are actually intertwined within each other. Okay? So let's just jump right in here. And so if I were to tell you the closest Earth-like planet, and you use the scales that we measure in daily life, like miles, for example, you might come out with a number that looks like this. And that reads as about, I think, 250 trillion miles. And so that only gets bigger if you're looking for other planets. And so as astronomers, we don't want to keep having to rewrite that big number every single time. And when you're dealing with these large numbers, it kind of becomes harder to understand what that number actually means. It's harder to comprehend how large of a number that is. And so in order to describe objects that are really, really far away from us, we have to be able to use the proper distance scales. Okay, so it's like you wouldn't use a ruler to figure out how far a car traveled. And so the same thing applies here in astronomy as well. So if I ask you this, right, how far is San Diego to San Francisco? Which response are you most likely to give? So would you say it's about an 8-hour drive, or would you say it's about 500 miles? So for me, and I'm guilty of this, I will tend to pick an 8-hour drive because that's something that we can easily relate to. We know what 8 hours feels like. And so we tend to judge how far something is based on how long it takes to get there. But if you think about the question, right, it's asking how far something is. So it's technically improper to give a response with units of time, when in reality, you should be giving a response in units of space, a distance, right? And so just to define the two, distance is a separation between 2 points in space. You have point 1, point 2, and you take a ruler, measure how far that is. That's your distance, right? And then time is a continuous forward progression of events from past, present, and future. So time only goes in one direction. And so the point of this is to say that distance is not the same as time. However, they're actually closely related to each other. Okay, so let's just explore that idea a little bit more. So going from San Diego to San Francisco, if you put that into a map app like Google Maps, it'll probably say it's about 500 miles, give or take. Yeah, and so the reason why you're saying it's about 8 hours is, one, you probably either experienced it yourself, or two, you could kind of guesstimate that, hey, if you're going 500 miles and you're going to be on the freeway for the most part, which has a speed limit of 65 miles per hour, well, you take the distance divided by the speed, which gives you the time. So therefore, 500 miles divided by 65 miles per hour, that's going to give you about 8 hours. Okay? And so in this one example, right, speed is basically what relates distance and time. When you travel 8 hours for 65 miles per hour, you will travel about 500 miles, just to wrap that around. Okay, so we do know that objects in space are much, much further away, But we also receive information from them in much faster speeds than we're used to. And so that's something that we can exploit to describe a new unit of distance. And so the fastest speed that information can travel is known as the cosmic speed limit, or in other words, the speed of light, the fastest speed in nature, right? So if you were to measure the speed of light, we have a pretty good idea of how fast light travels. It travels at about 300,000 kilometers per second, or 186,000 miles per second. So think about how fast that is. That is per second, right? And so, yes, that is incredibly fast. However, it does have a finite value to it, which means it's not infinitely fast. So again, when you start expressing numbers that are this large, the value kind of gets lost, the meaning gets lost. And so let's kind of try to put that into context. So just how fast is the speed of light? So again, from San Diego to San Francisco, 800 kilometers, 500 miles, and the time light takes to get there, if you do the math, right, it's basically 3/1000ths of a second, or 0.003 seconds. Okay, so if you want to put that into something more relatable, because 0.003 is such a small fraction of a second, you just do this. And so in those two times that I snapped my fingers, that was about 1 second. Light has already taken about 188 round trips from San Diego to San Francisco. Right? That is incredible. And so compared to us, we're slowpokes compared to light, because going from San Diego to San Francisco one way, right, and assuming there is no traffic, right, when you hit LA, when you hit the big cities in between, that's about 7.5 hours. Again, that's where the whole 8-hour estimation comes from. Okay, so again, and if you really want to appreciate and get a way better idea of how fast light travels and how slow you are compared to light, try walking there. You'll get a really good sense of how slow you are and how fast light is. Here's another way to put that into perspective. Light can circle the whole circumference of the Earth 8 times in 1 second, right? So you can travel the whole world 8 times in 1 second if you were able to move at the speed of light. So hopefully your brain is exploding right now, just like my little GIF here in the bottom left, because that's basically how I felt when I first learned about how fast the speed of light is. Okay, so now we can kind of play this game where I pick an object in space, and then I can tell you how fast light travels, because we do know roughly, how far these objects are. And so, for example, we know that it takes about 1 second for light to travel from the moon to the Earth, and that's also because we installed literal mirrors in there, and we shoot lasers to the moon, and we figure out, it takes about 1 second for that light beam to come back. Okay, and you've probably heard this one before. From the surface of the sun, it takes about 8 minutes for light to travel from the sun and reach us here on Earth. Proxima Centauri, it takes about 4.2 years. Proxima Centauri, by the way, is the closest star to us that is not our sun. So now, you're talking about 4.2 years. If you think about that, that's now kind of giving this impression that light is moving a little bit slow. And that's the closest star that is not our sun, right? And now, you're going further and further away. If you're trying to figure out how long it takes for light to travel within the Milky Way galaxy from one edge to the other, it's about 100,000 years. And that's light, and that's moving at the fastest speed possible. Now, if you want to go outside of our galaxy and you want to look at Andromeda, now that's going to be really, really long. That's about 2.5 million years. And so as you're looking at this table, right, and you should also think about a lot of the science fiction films you've watched before, where, some of the main characters go into light speed, they're going from different solar systems, different star systems, right, and it takes them like a fraction of a second to get there, right? When in reality, when you're moving at the fastest speed possible, right, I mean, going from here to the closest star to the sun, that's about 4.2 years. So that's a long, long time to travel. So again, sorry to burst your bubble, but that's just the reality of the situation, okay? All right, so here's another survey question. What is a light year, right? Is it the time that it takes for light to travel in the distance that the Earth travels around the sun? Or is it the distance that light travels in 365 days, or 1 year? Oh, excuse me, I think part A I said the time it takes. So it's the time versus the distance, right? So if you actually look this up on Wikipedia, which is a pretty reliable source of scientific information, if you ask me, 1 light year is the unit of astronomical distance equivalent to the distance that light travels in 1 year, which is, this many miles, 6 trillion miles, right? So keyword is distance in this case. And the reason why I highlight this is because people use light years in a very, more often than not, they use it in an incorrect way. Okay, so for example, when people or when businesses say, "Oh, we're light years ahead of the competition," right? Typically, what they mean that in the context of we're way ahead of their time, which isn't necessarily accurate because again, light year is a unit of distance as opposed to time. So it gives you that false impression that light year is a unit of time as opposed to distance. Okay, so just to clarify, a light year is a unit of distance, just like miles is, just like kilometers is. It's basically another unit of distance. And so now, knowing what a light year is, we can relate travel times with distances using the units of light. So, for example, if we know that light takes 1 second to travel from the moon to the Earth, then we can say that the moon is 1 light second away. And then going from the sun to the Earth, it's about 8 light minutes away, because that's the distance that light travels in 8 minutes. So it's a one-to-one correspondence with the light travel time and the travel distance using light units. So now when you go down further to these further objects, now you can start using the more commonly used unit for light years, right? So now you can say, oh, Proxima Centauri is 4.2 years travel time for light, so therefore it is 4.2 light years away, right? So it takes like 4.2 years to get there from us. So yeah, it's one-to-one, so it's a pretty easy way to remember the travel times. So there is some major implications with having a finite speed of light. So that means that if you're looking at Andromeda, right, if you see a picture of Andromeda, which this one is actually a picture of Andromeda, this is 2.5 million light years away. So that means that whenever you see a photo of Andromeda, a live picture of it, that's actually how it looked like 2.5 million years ago, because light had to travel 2.5 million years to get to your eyes. Okay, that's what that means. And so put that into perspective. If there was an alien in Andromeda that could actually see people on Earth, right, they're under the same laws of physics as us. So therefore, they would see the Earth as how it appeared 2.5 million years ago. So they would basically see humans when they first walked the Earth. And so, just to kind of summarize that again, nothing in nature travels faster than the speed of light. And so the information about events in the universe all travel at the speed of light. You know, like a star explodes, that information will travel at the speed of light to our eyes. And so the key point about that is that now the further out you look, the further back in time you're seeing. So we're basically seeing objects as how they looked when the light finally left them. And so if you think about that, right, like it's easier to think about that when you're looking at further away distances. So if a galaxy is 7, 12, or 14 billion light years away, then you're kind of looking back into time, right? But in principle, everything takes time to get to your eyes. So essentially what that means is that you're always continuously looking at the past, okay? If that makes sense. All right, so now we have a good handle of what light years mean, which is something that we're going to be using as a cosmic distance scale. And so now let's discuss the different distance scales for astronomy. And how we're going to do this is we're going to basically start off close, and close by I mean like basically Earth and Moon distance, and then getting further and further and further away to the point where you're actually going to be talking about the scale of the whole universe. Okay, so when you're talking about the scales of planets or moons, whether you're looking at 2 points within a planet or a planet to the moon, it's still actually commonly acceptable to use distance units that we're used to here on Earth, either kilometers or miles. So for example, Earth to moon distance is about 240,000 miles. So now at the scale of the solar system, if you're looking at how far away Mercury is to the Sun, Venus is to the Sun, and so on and so forth, we actually define them. It's more acceptable to define them using this new unit called the astronomical unit, or the AU. So the AU is defined as the average distance from the Earth to the Sun. And I say average because the Earth has a somewhat elliptical orbit around the Sun, so it's changing its axis. It doesn't have a consistent distance from the Sun. And so 1 AU is defined to have to be about 93 million miles. So the Earth is 93 million miles away from the Sun on average. And so by using the AU, you can actually get a good sense of how our solar system is structured. It's very easy to compare distances within our own solar system. So for example, if you look at the distance of Jupiter to the Sun, you can see that in the slide it tells you it's about 5.2 AU. So right off the bat, it's easier to understand that, hey, Jupiter is about 5 times further away from the Sun than Earth is. You can also take some more information about that, because if you look at the first 4 planets that are closest to the Sun, right, they're all enclosed from Mercury to Mars within about an AU and a half, 1.5 AU. Whereas you can see from Mars to Jupiter, there's a big 4 AU gap. And then from Jupiter to Saturn, there's about another 4 AU gap. So basically what that means is that the 4 inner planets are closely spaced together, whereas the 4 outer planets are further apart, much further apart. In fact, you can even fit all 4 inner planets in between Jupiter and Saturn, right? That's how far away they are separated when you're looking at the outer planets. So again, easier to compare between planet to planet or planet to sun distances using the AU. Okay, now let's zoom out. Let's go outside of our solar system. And so now, when you're talking about star to star distances, that has a big range. So you can go from a few light years. So for example, again, Proxima Centauri, a couple light years away, 4.2, to tens or hundreds of light years away if you're looking at further stars. But now, if you're talking about distances within our own Milky Way galaxy, well, it turns out that our galaxy is about 100,000 light years across, end to end. And if you look at where we are in our galaxy, if you look at the center here of the Milky Way galaxy, we're actually right here. And so we're about 28,000 light years away from the center, and then we're involved in this 230 million year orbit around the center of the Milky Way, which is kind of, again, incredible and mind-blowing at the same time, because usually we think of the solar system, the sun sits in place, and all the planets revolve around it. But in reality, the sun itself is actually involved in this very long journey around the Milky Way galaxy. Okay? So now let's keep zooming out here. Let's go outside of our Milky Way galaxy. And so the closest galaxy to us is the Andromeda galaxy. So the Andromeda galaxy is kind of like the Milky Way's sister or the twin galaxy, because they're both spiral galaxies and they're similar in very many ways. And if you're looking at how far away they are from each other, we mentioned this before, it's about 2.5 million light years away. And so this picture is actually a to-scale distance in terms of how big those galaxies are compared to how far apart they are from each other. Okay. Fun fact, Andromeda is actually one of the only galaxy that's going to be moving towards the Milky Way. Everything else is actually moving further from us with time. So in a couple billion years, the Andromeda and the Milky Way are going to be involved in a head-on collision. So that's going to be pretty incredible to watch if we're still around as people. Okay, so now let's actually zoom all the way out. And now we're looking at groups of galaxies called galaxy superclusters. So the Milky Way and Andromeda are actually part of a group of galaxies that are all bound together via gravity called the local group. It's about a group of like 50 galaxies or so. And then within that comes a bigger group of galaxies called the Virgo supercluster, and the Virgo supercluster of galaxies actually includes all of these galaxies you see here in the picture, and then more. Anyway, if you're looking at the distances between these galaxy clusters, now you're talking about tens of billions of light years away. Okay, so for example, the Milky Way's group, the local group, is about 65 billion light years away from the Virgo supercluster. So just as an example, so you're getting further out. Okay, so now if you keep zooming out, this is where it gets really interesting, because the universe, it turns out, forms this very uniform sponge-like pattern. Basically, this background that you're seeing here is how the universe looks like in the largest of scales. And so every single bright dot or pixel that you see here actually represents a galaxy like our Milky Way galaxy. And it's a very interesting picture because no matter where you look in the universe, it looks the same as long as you're looking at it in the grandest and the biggest of scales. And so these filaments of matter that I'm showing you right here are basically billions or hundreds of millions of light years long. So essentially you're encapsulating the whole universe in this one picture. Okay? All right, so that's about it when it comes to distance scales. In the next lecture, we're finally going to answer the question of where are we and what is now. See you guys next time.